Assalamu alaikum everyone, and today we are going to talk about acids and bases. So you're learning chemistry. What's the worst that can happen? Well, if you're in my friends' perspective, especially the intelligent students, the worst that can happen is failing. But the worst that can really happen in a lab is death. And I do not want to make light of this. They die lower than the average person, but they contributed so much to increase our life expectancy, so it's a necessary hazard. Now, after today's video, what does that have to relate to acids and bases? Well, acids melt your face. So work accidents happen in lab all the time because it's pretty safe to assume that anything there but water is dangerous. Now, what are we familiar with acids? Because we are familiar with it. Well, lemon, it has citric acid and sour. This is the first thing we learn about acids. It tastes sour and wait, give me a second. I can't do this right now. Okay, I may be feeling much better. So that's the first thing we learn about acids. It's extremely sour. Actually, in Latin, the word acid comes from a Latin word which means sour. Pretty easy to imagine. And also, acid is great at dissolving stuff and killing stuff and melting your face. Now, the opposite of the acid, a base. Bases taste bitter and are slippery, just like soap. Soap is indeed a base, if you didn't know that. Bases are also used as antacids, and also bases are not good and totally can melt your face. Sorry. Now, these facts we basically knew from childhood. At least I did. But now, remove them from your head. No, these facts don't exist. Remove these facts from your head. The most common acid and also the most common base is water. Basically, when we refer to acids, we refer to the model definition made by Johannes Bronsted. Johannes. Please tell me the correct pronunciation in the comments down below. And Thomas Lowry. They both make the exact same definition for acids and bases. And no, they didn't classify them with taste or how they look like. They define them, which is pretty impressive, as a wide range of molecules can be acids or bases, and defining them into one definition is hard. Now, the bronsted-lowry definition gives that the acid donates a proton and bases accept a proton. Also, a hydrogen ion is a proton because if it loses its electron, it becomes a proton. And proton transfer is huge in chemistry. Also, we write hydrogen plus, but in reality, hydrogen ions in an aqueous solution is always hydronium ions. Now, say a reaction of hydrochloric acid, an acid that we typically hear about, reacting with water gives a hydronium. Now we can easily see hydrogen water accepting a proton, and hydrochloric acid donating a proton. And for terminology, hydrochloric acid is the acid, water here is the base, and hydronium is the conjugate acid, and chloride is the conjugate base. Now, don't get confused, this has nothing to do with conjugative verbs. Conjugate acid term refers to the older definition of conjugal, which is used for prison visits for marital reasons. Yes, I looked it up on Google, and it means joined together. For every acid there is a conjugate base, and for every base there is a conjugate acid. But some aprotic substances, which are substances not containing a hydrogen ion, can have acidic behaviors, as the bronsted-lowry definition requires the acid or base to contain a hydrogen, but there are molecules without a hydrogen ion that also has acidity. This is where Gilbert and Lewis made his definition. Yes, he is the same Lewis from the Lewis dot structures video, and he defined bases is something that donates an electron, and acid is something that accepts an electron. A Lewis and a bronsted-lowry base is indistinguishable, but Lewis and bronsted-lowry acids differ. Bronsted-lowry acids need hydrogen plus, but Lewis acid just needs some atom in the molecule with partially positive charge. As look here, this is clearly a nitrogen donating an electron to a with a no hydrogen acid, and it accepts the electron, and this is only for Lewis acids. Something that can be a bronsted-lowry acid or base is amphoteric, like H2O. Now, the reactions we just saw are called acid-base reactions, and they are always in equilibrium because the conjugate acid and the conjugate base can easily combine again to form the original reactant. Sorry if I don't sound a lot enthusiastic, it's just eating the lemon is irritating human skin, because lemon's acidity is strong enough to irritate human skin. And fun fact, acid rains are actually as acidic as lemon juice, which, as I've demonstrated, is pretty acidic. So what were we talking about? Oh yeah, hydronium concentration. If we have the concentration bigger than 10 to the negative 7 equilibrium constant, it is an acidic solution. If hydronium concentration is less, then it's a basic solution, and if hydronium concentration is 10 to the negative 7, then it's a neutral solution. A strong acid can easily lose a proton as its conjugative base is really stable, or we can say it's a weak base. And a weak acid can make strong bases. To find out the strength, larger conjugate bases are more stable, and the acidity, say hydrogen being connected to halogens, hydrofluoride is less acidic than hydrogen iodine, because if we lose it, we get an iodide ion, which is more stable as it's larger than a fluoride ion, which is less stable. And also, the higher the electronegativity, the stronger the acid. So something like water losing its proton can happen any day, but say carbon losing a hydrogen will essentially never happen. There can be monoprotic and even polyprotic acids. Monoprotic can only lose one proton, but a polyprotic acid can lose multiple protons. A strong acid and a strong base gives a weak acid and a weak base. The strength can be determined by the pKa. The lower the pKa, the higher the acidity, and stronger acids deprotonate completely, weak acids deprotonate partially. And we saw deprotonation in my SN1 video. Now, the concentration of hydronium can sometimes be tricky and annoying. So we use pH, which is the negative log of the hydronium concentration, and the reason we use a negative log is logarithms. We know from our algebra series that it's the inverse operation of exponents, so it can take an annoying little number like 10 to the negative 7 and turn it into 7. And bases with POH is just that, but negative log of hydroxide. And another way we can determine it is that the KW, it is calculating the KW, and we can realize that pH plus POH will always be 14. So that's all there is to it. Sorry if this was a really long video, and we still have a lot more to cover about acids. So if you're having issues with my video, or I missed something, which I think I clearly did, cramping a lot of subjects into one video, so please let me know in the comment down below if you have any questions, and also if your friends have confusions in these similar topics, please share it to them. And please subscribe and like the video, and thank you for watching, and I will see you next time. Bye. Why am I doing this to myself?